The testing team consists of Joseph Bond, Bryce Egan, Lonnie Skiles, and Dewan Tawari. The problem we have is metals used in traditional manufacturing have known material properties that can be relied on when designing a part. Working with additive manufactured metals is very new to the industry, and we have to classify the material properties before we begin to design products from the material. We plan to determine the material properties through material processing and testing in order to provide a bracket that meets all the set specifications. We began this semester trying to improve the properties of the as-printed metal through heat treating. Heat treating leads to a more uniform grain sizes, which leads to better performance from the mechanical properties of the material. We outsourced our heat treating process to Temperature Processing Colorado. We had a 3-step heat treating process that we used to achieve the RAM 6061 T6 strength.
Why density test is important in that case? True density is the inherent properties of the materials. In relation to this, any vehicle going into the space has to withstand huge amount of vibrational and mechanical strength during the launch. So small pores or voids will lead to mechanical failure. To prevent this, density test is important. In that case, we implemented a standard formula to analyze the density of 3D printed aluminum from different location and orientation on the build plates. With the help of that, we were able to generate the result of density of as-built and heat-treated samples. Collectively, the values of the as-built and heat-treated samples were averaged individually. Both results showed less standard error of 0.051 for built and 0.0122 for heat-treated sample. This plot provides the comparison of our result with aluminum, which is precisely accurate to 2.73 gram per cc on average for both the treatments. With this, density test claims that 3D printed aluminum is solid and dense to be able to use as space hardware.
The purpose of testing the aluminum material under tensile loading is to see whether the 3D printed samples behave in a similar manner to the published results by Elementum for aluminum 6061 before putting it into production for the brackets. By tensile testing the aluminum, we will determine its modulus of elasticity and its strength failure points to prove whether it will be a suitable replacement in their brackets as opposed to traditionally manufacturing them. We tested 29 samples and measured the influence of the heat treatment, their orientation, and location on the printer. This is a distribution for one of the properties we found for the yield strength. The heat treating led to an increase in the yield strength in both the horizontal and vertical orientations. The T6 heat-treated 3D printed aluminum 6061 fell within the typical properties of standard aluminum, which indicates that these are safe to launch.
During launch, a satellite may be subject to many sources of vibration that could resonate catastrophically with mounted parts. To put it plainly, it's important to make sure that our bracket won't shake itself apart on takeoff. To do this, we perform modal analysis on all of the available bracket pieces to ensure that the fundamental frequency of the first vibrational mode was greater than the target value of 100 Hz. The analysis was performed experimentally with a PCB piezotronics modally tuned impulse hammer and the corresponding accelerometer. The National Instruments Elvis 2 Plus was used for data acquisition, and National Instruments Dynamic Signal Analyzer software was used for data logging. For each test, the accelerometer was attached to the top face of the sample with wax for adhesion. The samples were hung from the ceiling with fishing line to simulate free vibration. The accelerometer was connected to a signal processor before being routed into the Elvis 2 DAC, which was connected to a computer running Dynamic Signal Analyzer. In my experience running this software, I found these settings to be the best for generating detailed frequency graphs. These boil down to controlling the frequency span and dialing in the fast Fourier transform calculations. The roving hammer method was used in these tests rather than the roving accelerometer method due to the ease of setup. It is much easier to hit a sample in several different spots than it is to adhere an accelerometer to several different spots. Each part was struck on each of its 6 faces while the accelerometer stayed in the same position. Each of the 6 tests were then exported as a text file for later analysis. Each set of data is plotted so that the obvious peaks where the modes are can be found. A range of frequencies surrounding the first peak is found, and then that range is searched for the maximum magnitude value. The frequency that corresponds with the maximum magnitude is the first mode of vibration. To verify that the accelerometer was working properly, a set of tests was first run on an extruded aluminum calibration bar of known dimensions. A model of the bar was created in SOLIDWORKS, and a free vibration simulation was run on it. The results from SOLIDWORKS and from the hammer were then compared. Since they were within an acceptable margin of error, we could be sure that all of the hardware was working correctly. Here's the data from each sample. Since each part has a fundamental frequency above the target value of 100 Hz, we can conclude with a high degree of confidence that the finished product would resist the pitfalls of resonance during launch. In conclusion, we showed that 3D printed aluminum does not possess an excess of pores, strength values match those of typical 6061 T6, and that our printed parts met Lockheed Martin's modal analysis requirements. This indicates that aluminum printed via a selective laser melting process can be a suitable material for flight-ready parts.